if we place a charge of plus Q on one plate and negative Q on the other plate, what's going to be the electric field between them? So using that electric field, we can now come up for the formula of what is the potential difference between the plates. Okay? So what's the electric field between two plates? Well, again, we did that in chapter 24 using Gauss's law. The electric field between two plates was sigma over E0. Right? Remember, it was constant. And each plate creates an electric field equal to sigma over 2E0. When you add sigma over 2E0 plus sigma over 2E0, you get sigma over E0. Right? And the electric field outside is pretty much 0. So it's confined, the electric field is confined to the inside. Okay? So now, if I want to find the potential difference, let's say I want to find the potential of that minus this. So we'll call this V2 minus V1. So I want to find the potential of the positive plate is going to be higher than the potential of the negative plate. So then I'm going to integrate the integral, the E. Well, since I'm integrating it this way, my dr and my E are opposite, you see? So I'm integrating it this way, so their dot product is going to be negative E dr from 1 to 2. And the two negatives cancel, and you get positive, and the E comes out of the integral. Right? So the two negatives cancel, you get a positive, and then the integral, the E is constant. It comes out of the integral, and the integral of dr is d. And sigma is equal to the charge per area of the plates, the surface charge density. QD over A is 0. So now, if I wanna calculate the capacitance of the capacitor, I divide the charge. See, I'm using the definition here. I divide the charge on either plate divided by the potential difference between the plates, and the Q and the Q cancel, and you get A is 0 over D. Which is, remember, the formula that we used for our third lab, right? That was the capacitance lab. So that was the formula that we used. A is 0 over D. Notice a couple things here. The capacitance of the capacitor does not depend on how much charge you place on it. Now, if you go to the definition, it will make you think that the capacitance actually depends on charge. The more charge you place on a capacitor, the more the capacitance, right? Doesn't it falsely make you think that? C is Q over delta V. So if I place more charge on it, hey, I can make its capacitance bigger. No. Because if if you place more charge, what happens to the delta V? It also goes up, right? So if you look here, the delta V itself depends on Q. So the Q and the Q cancel. So capacitance should not depend on how much charge you put on it. The capacitance should only depend on the geometrical measurements of the capacitor. See? And that's true. It should only depend on the, let's say, the surface area and the distance d. Let's see if it makes sense. This is telling us if the surface area is bigger, then the capacitance gets bigger. Right? In other words, if I want to, let's say I have a 3-volt battery. By the way, this is the symbol of capacitor in the circuit. Okay, just 2 plates like that, that's it. So if I take a 3-volt battery, so in other words, this is fixed. Let's say this is 3 volts. And I hook up a 3-volt battery to a capacitor. This is telling me that the more bigger the surface area of the capacitor, its capacitance will be higher, and therefore it will be able to store more charge. If I hook up a 3-volt battery, if the surface area is bigger, it's going to be able to store more charge because its capacitance is going to be higher. So does that make sense? Well, yeah, of course. If the surface area is bigger, there's more surface area, and it can, the battery can now bring in more charge, and it can fit all those charge on a bigger surface area. So geometrically, it should make sense. And the D, that's a different thing. It's telling me if the D is closer, I can this capacitance will be higher, right? And I can store more charge. So if these 2 plates are closer, and the potential difference between them is 3 volts, you see, I can now store more charge. If I separate the plates, okay, and now I hook it up to a 3-volt battery, what's going to happen? Not as much charge is going to come in. You know why? Because if the plates are far apart, the potential difference between them is already large, right? Potential difference between plates depends on the distance between the plates. Look here. The potential difference between the plates depends on the distance. So if I take 2 plates and I separate them, I'm already increasing their potential difference. And if I hook that up to a 3-volt battery, the 3-volt battery is going to say, okay, set up 3 volts of here. So since their potential is already high due to the fact that they're far apart, not as much charge is going to come to that capacitor, because their potential is already going to be high due to the fact that their D is big. So that explains why as the D goes down, the capacitance goes up, and as the capacitance goes up, the charge goes up. So if you want to store a lot of charge on a capacitor, make it big and make the 2 plates close. Okay? Okay, then the next time we'll do this, we'll go into spherical capacitors, cylindrical capacitors, and then we'll go into dielectrics. I'll show you what happens when you put a dielectric in there. It makes the capacitance go up even more. And I'll talk about energy stored in a capacitor, the formula. I'll go over the equation for the energy stored in a capacitor, and then we'll start transitioning into circuits and how the capacitors add up in series and parallel. We'll do all of that. Okay, good.